My name is Alphonsus Adu-Bredu. I present here today our work on probabilistic inference in planning for partially observable long horizon problems. Robotics research has long envisioned robots capable of performing household tasks, as shown in these videos of teleoperated robots. A robot tasked with such an objective would have to be capable of planning actions over large state and time horizons. It would also have to account for uncertainties in its perception and knowledge of its environment. Some sources of partial observability include object pose estimation noise, occlusion, and noisy robot joint configuration, resulting in stochastic effects of the robot's actions. In view of these challenges, we propose Shy Cobra as an approach for long horizon planning under uncertainty. Given a high-level goal and a prior belief, Shy Cobra plans high-level actions to accomplish the goal, and then probabilistically infers continuous action parameters needed to execute the plan, and updates its belief and replans whenever actions fail to accomplish the desired effects. A brief description of our approach is as follows. Given a set of high-level goals and a prior belief obtained from the robot's observation, a symbolic planner plans a sequence of high-level actions in the form of a plan skeleton to achieve the goals. The plan skeleton is composed into a factor graph called the constraint network, which is made up of variable nodes and constraint nodes. The prior belief is used to initialize the variable nodes in the constraint network with particles, which represents the robot's initial belief of the variable nodes values. Non-parametric belief propagation is used to pass messages between the nodes of the constraint network until there is convergence to constraint satisfying beliefs at each of the variable nodes. Constraint satisfying parameter values are sampled from the variable node beliefs and are assigned to free parameters of actions in the plan skeleton. The plan is then executed by the robot. If all actions in the plan are executed successfully, we are done. But if an executed action results in an unexpected effect, the robot observes the world, updates its belief, and repeats the cycle. How do we compose the plan skeleton into a constraint network? Each symbolic action in the plan skeleton is associated with a set of free parameters that ground the action and a set of constraints that should be satisfied by the free variables for the action to be successfully executed. The example above shows a plan skeleton for a pair cooking task and depicts the constraints and free variables associated with every symbolic action in the plan. For instance, the pick action has free variables Q, P, G, and T, which represents the robot's joint configuration, object pose, grasp pose, and joint trajectory, respectively. It also has stable, grasp, and kin constraints that enforce the stability of the object pose, grasp stability, and the kinematic feasibility of the joint configuration, object pose, and grasp pose. We represent the plan skeleton as a factor graph made up of two kinds of nodes, constraint nodes and variable nodes. Each constraint node represents a constraint in the symbolic actions and is connected with edges to variable nodes that represent free parameters associated with that specific constraint. This constitutes the constraint network. Given the constraint network, we initialize observed variables non-parametrically with particles that represent the robot's belief from the noisy observation. Given the observed variable beliefs, We use specialized samplers to sample prior beliefs for the remaining variable nodes, also represented non-parametrically as particles. Using a non-parametric belief propagation approach, we compute two kinds of messages: the variable to constraint message, which is the message sent from a variable node to a constraint node, and a constraint to variable message, which is the message sent from a constraint node to a variable node. Both kinds of messages are also non-parametrically represented as particles. Computing variable to constraint messages involves finding the product of all incoming messages to the variable node, except that from the destination constraint. Computing the constraint to variable message involves rewriting particles of incoming messages to the constraint node using specialized constraint functions designed for each type of constraint and taking the max product of the reweighted messages. After each iteration of message passing, the belief of each variable is updated as the product of all incoming messages to the variable node and is resampled. The computed messages are passed along the factor graph for a pre-specified number of iterations. The maximum likelihood estimate of each variable node belief is assigned to the corresponding action parameter variable, and the action is executed in turn. We show a demonstration of our approach on a cooking task in a simulated kitchen environment. The task here is to cook and serve a meal. The sources of uncertainty are the uncertainty in the object pose estimation and the uncertainty in the robot's joint configuration estimation. The robot first tries to retrieve the pair. Its prior belief of the location of the pair is uniform across all three drawers, so it first opens a drawer at random. Once it doesn't find a pair, it updates its belief and opens another drawer. Once the pair is located, it grasps the pair, closes the drawer, moves to the sink to wash the pair, and places the pair in the saucepan. Each of these actions are performed using the inferred continuous action parameters like grasp poses and joint trajectories. The robot then tries to grasp the cup. The first grasp attempt fails. The robot receives new observation, updates its belief, replans, and infers new action parameters. The robot then reattempts the grasp action and succeeds. The robot fills the cup with water, pours the water into the saucepan, cooks the pair, and serves it at the dining table. We examine the performance of Shy Cobra on tasks under conditions of increasing object pose estimation and joint configuration uncertainty. We compare Shy Cobra with SSReplan, a state-of-the-art task and motion planning approach, which is only capable of accounting for object pose estimation uncertainty. Shy Cobra makes fewer errors and replanning calls, and as such spends cumulatively shorter time planning than SSReplan. The major limitations of Shy Cobra are: firstly, Shy Cobra requires tuning of hyperparameters like number of particles and number of iterations, which can be tedious. Secondly, constraint functions are tedious to hand design. A needed improvement could be to learn these constraint functions from data or from experience. Finally, the planning time and number of iterations needed for convergence increases significantly with increased uncertainty, as shown in the plot. In summary, we proposed Shy Cobra as an approach for long horizon planning under uncertainty. Shy Cobra employs non-parametric leaf propagation to infer constraints satisfying continuous action parameters needed to execute actions in a plan. The factor graph formulation and our use of non-parametric leaf propagation makes our approach capable of accounting for arbitrary sources of uncertainty and uncertainty models in action parameters. We also demonstrated Shy Cobra on kitchen tasks and examined its performance on tasks with increasing uncertainty. Thank you.